Okay, so I want to review the practice quiz that I gave you in class. I'll probably post a blank copy of this as well. When we talk about water potential, remember that water potential is going to push water from an area of high water potential to an area of low water potential. And that water potential is made up of two factors. One is the solute potential, which we can calculate using this formula. All of this will be given to you on the AP exam and also given to you on the quiz. So, and then plus the pressure potential. Okay. And okay, so I think we're ready to start here. The first problem isn't really one where you're calculating water potential, but it's just asking you about if what's going to happen to the cell. So since no actual numbers are given here, what I like to do is put in some numbers. So it's telling me that we have a plant with a higher water potential in its surrounding environment. So I'm going to put in just an arbitrary number here, -2 for my cell. This is my cell. And my environment, I'm going to put in a -4, which is a lower water potential. Again, we have some -2 is a higher number than a -4. So that means that the cell has a higher water potential, like it says in the problem. So, and it's not have any pressure potential to deal with in this question. So again, water potential is going to move from an area of water from an area of high concentration to an area of low concentration, not concentration, potential. Or in this case, water is going to move from the cell to the environment. And that should be explained here, but we have another question that's being asked here is the cell hypertonic or hypotonic to its environment? And what I like to ask is like, which one is saltier? Which one has got more solutes here? And the one that has lower water potential means that that is because it has a lot of solutes dissolved in it compared to the other one. So in this case, our cell is going to give up its excess water in comparison to these two to its environment. So the cell losing water, the cell is hypotonic. The cell is hypotonic to the environment. If you put cells in a environment and they lose water, it's because they are in a hypertonic environment. But then we're talking about the cell. The cell is hypotonic to its environment and it will lose, the cell is losing water because water moves from an area of high concentration to an area of low concentration till eventually they reach equilibrium. Okay, so this next problem here is the same as 6B, I believe. So I'm going to reserve that for when we talk about 6B. All right, next question here is comparing two water potentials, I believe. And let me get my calculator ready here because I know I'm going to need it. And so again, we're going to use to calculate the water potential and solute potential, we're going to use to calculate the solute potential negative I for ionization constant, C for concentration, molar concentration, R for the pressure constant, and T for the temperature in degrees Kelvin. So that is going to all be equal to our solute potential. So for the first cell we have here, it's going to be it's telling me to use an ionization constant of 1 for both. It's not telling me what I'm putting them in, but so I'm going to use -1 times the molar concentration of 0.35 times the pressure constant, which is going to be 0.0831 times temperature in degrees Kelvin. So it's 22 plus 273 is going to be equal to 295, I believe. Hopefully I was right there. And then let me go ahead and put this into my calculator. And so I have a -1 times point. Make sure you can see that. Times 0.35 times 0.0831 times 295, all equal to a -8.58 for -8.58 for that first cell. And that's in bars. And then for my next one, it's going to be equal to, and it says to use -1 for both, or to use 1 for both. And it's going to be times 0.28 molar times 0.0831 times 295 are going to be equal to, all of that is going to be equal to -1 times 0.28 times 0.0831 times 295. All of that is equal to a -6.86 bars. And now we have to ask ourselves which one of these has a higher solute potential and which one has the lower. So we have a -8.58 versus a -6.8. So this is the higher number and this is the lower number. So water is going to move from, this must be the cell, and this is the environment. So that water is going to move from the environment to the cell. Okay. I think that's that on that question. Let's move on to the next one, which I did in class, but if you weren't here or I went too fast or we didn't finish it up, let's take a look at it again. And, or I messed up like I did in second period. Okay, so first thing, when we're looking at this plot, we're trying to figure out the molar concentration of the potato. So we're looking for the period or the point where it does not gain or lose any mass. So on this plot, it looks like that's around a little bit past 0.35. So they're going to call this 0.36 molar. And we're going to use that in our formula. Okay. So we're dealing with sucrose here. I'm going to drop this down here. And we have a -1 because we're looking at sucrose first. This has sodium chloride later in the problem, times the molar concentration, which we just calculated to be 0.36 molar, times the pressure constant, 0.0831, times our temperature in degrees Kelvin. So that looks like it's 22 plus 273, 295. And all of that is going to be equal to we have -1 times 0.36 times 0.0831 times 295. Oops, that's too many nines. That's wrong. -1 times 0.36 times 0.0831 times 295. Did I do 0.295? Negative. I'm still missing my negative here. -8.83. That's the water potential of the potato. Now we're going to put it in the beaker and we want to know what happens. So we're going to put it in to a beaker of sodium chloride. So this is now we're using a -2 as our ionization constant. Make sure this is sharper. -2 times our molar concentration, which is given as 0.2. Could hear the band. Some of you guys might be out there playing. And then we have our pressure constant times 295, same temperature, and all of that should be equal to -2 times 0.2 times, what a -2 times 0.2 times 0.0831 times 295. Oh, that band sounds great. I love it. Every 10th period, I get to hear it. -9.81. All right. So again, we're going to ask ourselves which one of these is the higher number, which one is the lower number. So this number is higher, this one is lower. So, and this is the potato, and this is the beaker. I just call it any environment beaker. I'm assuming that's what we're putting it in. And therefore, water is going to leave the potato and go to, it's going to leave the potato and go to the beaker. So it's going to lose mass. All right, good. That was pretty straightforward. All right, let's look at number 5. Number 5 is a little bit different because we're going to account for a pressure potential here difference. So we have, remember that water potential psi is equal to the pressure potential plus the solute potential. So we have to calculate both, or we're going to use the pressure potential that's given to us here. So in this case, we have sodium chloride. So we're going to do a negative, to do my solute potential, a -2 times my molar concentration of 0.25 times our pressure constant of 0.0831 times a temperature in degrees Kelvin. And in this case, we're looking at 20 degrees Celsius. So that is going to be, sorry, you had to hear that. That is going to be equal to 293. All right. And when we put that into the calculator, we have a dead phone. Get another calculator because I have one. Pause this for a second, plug my phone in. Okay, so I found a calculator here. Hopefully I know how to use it. Can I just use this for a minus? No, is there a minus? Is there a negative symbol? Why can't you just use a minus? Is it 2? I don't know how to use a calculator. My goodness. Oh, here it is, I think. -2, there we go. Times 0.25 times 0.0831 times 293 is equal to a -12.17. So that's for this here. However, we have to add to this the pressure potential, and that's also negative. So it's going to be a 0.6 rather, that makes a difference, plus a negative 12.17. Therefore, this is all going to be equal to a negative 12.77. That's the water potential. Because remember that it's going to be equal to your pressure potential plus your solute potential. All right, good. All right, last problem here is about the Titanic. And let me see if I can zoom in so that's a little sharper. Okay, so we need to figure out the water potential or the solute potential of the seawater first. So it's going to be a negative 2 because it's sodium chloride times our molar concentration 0.5 times our pressure constant 0.0831 times our temperature in degrees Kelvin. So this is going to be 273 minus 5 because it's a negative 5 degrees Celsius. So this is going to be equal to 273 minus 5. Yeah. And all of that is going to be equal to, let's see here. We have a negative 2 times 0.5 times 0.0831 times 268 give me, ooh, that's a big water potential, which makes sense because it's salty water. 22.2, let me just call that 22.3. All right, now we're going to calculate for our cells, which is this problem here is the same as the one that was on the previous page. If you did it there, then you got it. Or you could practice it again, but we have a negative 2 again times, that's our molar equivalent of sodium chloride in our own cells, times 0.15 times 0.0831 times temperature is going to be different because we have body temperature. So assuming that you got put in, your body's still trying to maintain body temperature. So we're at 37. So 273 plus 37 should be 310. All right, so all of that is going to be equal to a negative 2 times 0.15 times 0.0831 times 310 give me a water potential of our cells to be a negative 7.7. Negative 7.7. All right, again, I like to ask myself which one's high, which one's low. So this is the high water potential and this is low water potential. I think you already know the story here of what's going to happen if you were to put your cells into seawater, but there's a big difference in your water potential here. So these cells are going to lose the cell. This is a cell. This is the C. We're going to go from water potential of high to water potential of low. And a lot of water is going to be lost from the cell to the seawater. Yeah, so that's what's going to happen. You're going to dehydrate quicker than if you didn't drink any of the water at all. And that's water potential. Let me know if you have any questions. Good luck.